Hello everyone, my name is Lisa Huang. Today, I would like to share with you some exciting work we did at UC San Diego, validating AI-generated code with live programming. Our work focuses on the task of validating AI-generated code, that is, deciding whether it matches the programmer's intent. I'm going to show you that the task of validation is burdensome. Here's a code example, where the middle section of the code with a green background is generated by the AI. How do we know if the code works? And how do we validate it? There are many validation strategies, the most effective being validation by execution, that is, running the code and inspecting its behavior via print statements. This strategy, however, is manual and time-consuming. For this particular code snippet with 2 for loops, imagine how many print statements one would need to add to inspect the code behavior. Validation by execution also involves a lot of context switching, forcing the programmer to rotate among editing code, running it, inspecting its output, checking against their expectation. So, what might help validate AI-generated code? The technique of live programming comes to mind. Live programming is a paradigm where the programmer gets immediate feedback on the program behavior all the time. For example, in projection boxes, a live programming environment, once the programmer has a program where A is 10 and B is twice of A, they immediately see boxes attached to the program showing the runtime values of the variables, 10 and 20. If they change B to be 3 times of A, then the boxes and runtime values inside update immediately, showing that B is now 30. Our work explores whether and how live programming can assist validation of AI-generated code. To that end, we built a programming environment that combines projection boxes and an AI-powered assistant. The assistant gives programmers multiple code suggestions that they could choose from in the suggestion panel on the right of the environment, and they could inspect the behavior of the suggestion via live programming. A full demo of our tool can be found along with our paper in the ACM digital library. With this environment, we ran a study where programmers validate AI-generated code, hoping to understand how live programming affects the over and under-reliance on AI, validation strategies, and the cognitive load of validation. Through our study, we found that by lowering the cost of validation by execution, live programming mitigates over and under-reliance on AI-generated code, reduces the need for code examination in some tasks, and lowers the cognitive load of validation in some tasks. But how did we get to these findings? We recruited 17 participants with a mix of occupations and Python usage frequencies. We used block randomization to assign participants into 2 groups while balancing task order and selection and their expertise. We had 8 participants in group LP, where they completed tasks with AI-generated code and the projection box's live programming environment, and 9 participants in group no LP, where they used a terminal-like panel for code execution as opposed to live programming. We used 2 categories of tasks in the study, fixed prompt tasks and open prompt tasks. In each fixed prompt task, participants were given a fixed set of 5 AI suggestions that are intended to solve the entire problem. In open prompt tasks, participants were free to invoke the AI assistant however they wanted. Among the 4 tasks we used in the study, pandas and bigram are a fixed prompt, while boxplot and string rewriting are open prompt. In addition, half the tasks across both categories are API heavy, where task solving involves a heavy use of Python libraries, and the other half are algorithmic. Each study lasted less than 2 hours on Zoom, where each participant completed both fixed prompt tasks, 1 open prompt task, and a semi-structured interview. We collected the following data from our study. The success of each fixed prompt task, including each participant's subjective assessment and the objective assessment. Participants' cognitive load after each fixed prompt task, the task duration of each task, and validation-related quotes and behavior. The rest of the presentation summarizes highlights of our findings based on the collected data. We first looked at the effects of live programming on the over and under reliance on AI during validation. From the fixed prompt tasks, we found 6 instances of unsuccessful validation, and they're all from the no LP group. Specifically, there are 3 instances of over-reliance, where participants incorrectly trusted the AI suggestion, and 3 cases of under-reliance, where participants did not trust the AI suggestions enough and ran out of time when validating the code. Here we show some examples of over, under, and proper reliance on the AI. A no LP participant who over-relied on the AI relied on the AI-generated comments that incorrectly described the code for validation. Another no LP participant who under-relied on the AI, when facing multiple AI suggestions that were correct, chose not to use any of them, and instead wrote their own solution to the task based on parts of the suggestions. In contrast, all LP participants trusted the AI-generated suggestions properly, with one person commenting that live programming saved them the effort of writing print statements for examining code behavior. Indeed, the immediate feedback on program execution in live programming helped LP participants form an appropriate understanding of program behavior and resulted in no observed instances of over or under reliance. We thus derived that by lowering the cost of validation by execution, live programming mitigates over and under reliance on the AI-generated code. Next, we examine the effects of live programming on validation strategies. This box plot shows the percentage of time participants spent just reading the code suggestions in the fixed prompt tasks, where the blue boxes represent LP participants and the orange boxes represent no LP participants. We see that LP participants spent significantly less time reading just the code than no LP participants in Pandas, a task amenable to validation by execution. Instead, they spent more time inspecting the runtime environment via live programming and thus understanding program behavior, as this quote illustrates. Although we have other findings regarding the effects of live programming on validation strategies, here we want to highlight that it reduces the need for code examination in tasks amenable to validation by execution. Finally, to measure the effects of live programming on the cognitive load of validation, we used NASA TLX cognitive load metrics as plotted in this box plot. The blue boxes refer to the LP group, and the orange boxes are for the no LP group. We found that in the Pandas task, the measures of the LP group are lower. In other words, participants experienced a lower cognitive load in the Pandas task. We didn't observe this in Bigram, an algorithmic task. Recall that the Pandas task is more amenable to validation by execution. As such, we conclude that in such tasks, live programming reduces the cognitive load of validating AI-generated code. Due to the time limit, I only gave you an overview of the highlights of our work. We did a study with 17 participants and identified 3 ways of how live programming could help validate AI-generated code. For more information, please check out our paper, as well as the code for our tool and the study materials linked below. Thank you.